All right, so we're in section 2.5, and in 2.5 what we're doing is we're looking at solving certain differential equations using substitutions. And the idea here is kind of similar to what you learn in calculus when you learn about U substitutions. When you first learn about integrals in the fundamental theorem of calculus, you learn that you're looking for an antiderivative for whatever function you're trying to integrate. And you'll run through some pretty standard examples. You'll integrate x squared or secant squared or something like that. Things with things that are recognizable as derivatives of other functions. And so it's very straightforward to take the antiderivative. But you see very, very soon that most integrands that you can be dealing with don't really look immediately familiar as the derivative of something. And so the idea there is you use U substitution, a change of variables, to simplify the integrand in a specific way so that it reduces to something that does look like a familiar derivative. Here we're doing something kind of similar. So up until this point, we've talked about three different methods for solving first order ODEs, depending on the form that they take. So we have separable equations, which we can solve by separation of variables. That's one method. Linear first order equations, and we can solve those using integrating factors. And then exact equations, which we went through the process of solving those in the previous section. A lot of first order ODEs don't fall into any of those categories, but after making some kind of variable substitution, that might open up a door that allows you to use one of those properties, or those methods, not properties. So we're going to talk about three different types of solutions here depending on the form of a differential equation. And the first one is going to concern something that we call a homogeneous equation. Homogeneous is a term that shows up a lot in both this class and in linear algebra, and it means something different here than it would in a linear algebra class. So if you've taken linear and you're looking at this and you're thinking that looks nothing like a homogeneous linear system or something like that, it's because the term is being used in a different way here. One thing I will mention before we go any further, a lot of people will pronounce this homogeneous, and you're not wrong to pronounce it that way either. It's weird. I've looked at a lot of different YouTube videos surrounding this topic just to see how people are pronouncing that word. I've talked to a lot of people, and it's almost a 50-50 split. To me, it seems like half of the people talking about this topic will say homogeneous, the other half will say homogeneous. So I'm just going to say either pronunciation is okay, and let's not get hung up on that. So what is a homogeneous function? Or more specifically, we call it a homogeneous function of degree alpha. So a function that can be homogeneous, it's a two-variable function, f of x, y, and we call it homogeneous if it has this function. If I make a substitution for these two variables, tx and ty, then this is actually a typo here. There should be an f here. It's a little sloppy, but that is equal to t to the power of alpha t to the power of alpha times f of x, y. So in a certain sense, you can pull the t out of your arguments here, and it comes out as a t to a specific power alpha. Whatever that alpha is we call that the degree of that function. So that's the definition for a homogeneous function of degree alpha. Now, if you're not used to working with things in this kind of functional notation like this, an example helps make things a little more clear. So we're given a function here, f of xy equals y cubed minus 2x squared y. Our job is to show that this is a homogeneous function of degree 3. So what we do is when we make this substitution, we look at f of tx ty. What is f of tx ty? Well, this is telling me to substitute tx everywhere I see an x, ty everywhere I see a y. So that y cubed becomes ty cubed. And that minus 2x squared becomes minus tx, 2tx squared, and then that y becomes a ty. Okay? Now, if I were to, combine some stuff here, use some exponent properties and multiply things together, it's very easy to see that this is equal to t cubed, y cubed right here. This is equal to minus 2. I'm going to get a t squared when I use this exponent, and then multiply that to another t here, and I'm going to get a t cubed. I also have an x squared and a y that's going to pop out of all of this. Okay? But if I were to factor that t cubed that's appearing in both terms there, factor it out, I get t cubed times y cubed minus 2x squared y. Now notice the stuff in parentheses here is how we defined our original function. And so this is equal to t cubed times f of x y. Okay, so you can see how this fits the definition of a homogeneous function here. I plug a tx and a ty in for my arguments, and in a certain sense that t comes out, but it picks up a power of 3 along the way, and then that's being multiplied to f of xy here. So that's what it would take to show that this is homogeneous of degree 3. Why are we talking about these types of functions? Well, if you have a homogeneous function of any degree, there is a particular substitution that you can use to actually, sorry, let me back that up. We have to be talking about a differential equation first. So let's take a look at this. If you have an ODE and it's in differential form, I'm missing a dy here. A couple of typos on this one. If you have an ODE in differential form the way we do here, then if you also are able to show that the m of xy here and the n of xy here are both homogeneous functions of the same degree, and they have to be of the same degree, then there is a technique, or more accurately, a substitution that we can make that reduces this to a separable equation, the easiest kind to solve. And to show you why that works, let's just suppose that that's the case. We have m of xy and n of xy, and they're both homogeneous functions of degree alpha, let's say. So in that case, one thing we can do is if we take m of xy, I can write this in a specific way. X is equal to x times 1, and y is equal to x times y over x. Clearly, right? The purpose behind doing this is now I have x times something and x times something in each of my arguments. That x in each of those arguments is going to play the role of the t that shows up in this definition for our function. Because this definition implies that this property is true for all values of t, including, assigning another variable to that, x. So writing this way allows me to pull that x out because this is a homogeneous function of degree alpha, and it comes out as x to the power of alpha. What would be left? Well, the 1, which we see here, and y over x. But if I were to call y over x u, then this becomes m of 1u. And I can do something similar for my n of xy. You can read through this and see what I'm doing here. But what does that do for each of these functions? Well, if I make a variable substitution, if I define u to be y over x, it's taken this function of x and y, which we don't know if that can be written as a product of a function of x times a function of y. And we've made a variable substitution in such a way that the result is a product of a function of x to the power of alpha, times a function of u. Notice that even though this is it has the notation of a two-variable function, the only variable appearing here is actually u. So this is a product of two single-variable functions, and if I do the same thing over here with n, the function x to the alpha is the same in both cases. That would allow me to factor that x to the alpha out up here, and after rearranging things, I get a separable equation out of that. Alternatively, I could have, instead of pulling an x out of each term in here, I could have pulled a y out and made a similar substitution. I'm using a v for that, but you can kind of read through this and see the similarity. So that's the idea, is we use these substitutions, or we can also call it y equals ux and x equals vy, to introduce new variables that'll help reduce this thing to a separable equation. Okay? So let's try that with an example. Okay? This is in a differential equation. It's in differential form, which is what we need for these homogeneous functions. And first thing I want to do is show that both this function here and this function here are homogeneous of order 2 in this case. So for example, if I define m of xy to be that first function, y squared plus xy, then that would imply that m of tx ty is equal to ty quantity squared plus tx times ty. And it's very easy to show here that this is equal to t squared times y squared plus xy, or in other words, t squared times m of xy. It's homogeneous. It fits that definition, right? If I also define n of xy to equal this second function here, x squared, that's equal to x squared, that implies that n of tx ty is equal to tx squared, which is equal to t squared x squared, or t squared n of xy. I can see very clearly that that's what this is. So these are both homogeneous of linear or of order 2, allowing me to use this technique. So what I'm going to do is define a variable substitution. And again, on this page here, we said that if we have a homogeneous function, or a DE in differential form, where both of these are homogeneous functions, then either of these variable substitutions will do what we want to do. Now, technically, regardless of what these functions are, either variable substitution will do the job. But depending on which one you use, it may give you more difficult functions to deal with. So I'm going to try the first one here, and if it leads me down a path that's not helping, I'll try the other variable substitution. So I'm going to set y equal to ux. Okay? Now, that gives me something that I can substitute into the y's in my equation, but notice I also have a dy here, which I'll need to deal with as well. So I need to determine what dy looks like. Here I have that y is a product of two variables. So dy, to evaluate that, it's going to look like the product rule. I'm going to get dy equals u dx plus x du. Okay, we're treating that like a product of functions, and differentiating to get dy is going to produce a something that resembles the product rule. Okay, so here we can make some substitutions now. So for anywhere I see a y, I'm going to substitute ux, and for this dy here, I have to substitute this new expression with these differentials. That way all of the y's are going to drop out. So what happens now? Y squared becomes ux squared plus xy. That's the same as plus x ux. Okay? And that has a dx here, plus x squared times dy, which now has this new form, u dx plus x du. And that equals 0. Okay? Next thing I want to do is collect the terms that have dx's in them and the terms that have du's in them, and split that up so that this thing is now in differential form, but with the new differentials dx and dy, or du. So notice both of these terms have a dx in them if I were to distribute. But there's also this dx term that's going to come from multiplying this x squared in. So I'm going to multiply that x squared into both of these terms, and then take that and regroup it with these guys over here. I'm also going to simplify some things here. So notice what we have here. I'm going to have an x squared that shows up here, an x squared showing up here from this x times x, and an x squared showing up there. Let's multiply or factor that out. That becomes x squared times, I'll have a u squared plus u plus another u right here. So plus u squared plus 2u dx. Okay? Also, when I distribute this x squared in, I'm going to get an x cubed du, and that's going to be the only term with a du in it. X cubed du. Set that equal to 0. Okay. Now we want to think separation of variables. This is now a separable equation, and that was the whole idea in the first place. Let's subtract that guy over. X squared times u squared plus 2u dx equals negative x squared du over here. So I can divide both sides by, oh, that should be cubed there. I can divide both sides by negative x cubed, and divide both sides by u squared plus 2u. That's going to give me negative 1 over x dx on this side equals du over u squared plus 2u on this side. I'd like to integrate both sides here, and looking at this guy, that's the same thing as du equals u times u plus 2. I would need to use partial fractions on this guy again, and for the sake of time, I'm not going to walk through doing partial fractions. I'm just going to take you to the, I'll do that in the next step. This is, I want to integrate both sides, negative 1 over x dx equals, after partial fractions on this guy, we're going to get 1/2 times the integral of 1 over u minus 1 over u plus 2 du. Okay? Please, take the time to get from here to here on your own. This is one of the easier partial fractions examples. And just, again, I've said this before, just because I'm not going through all of the work that the integration requires does not mean that I wouldn't want you to do that on a test or something. I want you to take the time on a test to show me the work getting from here to here, but, that's prerequisite stuff, so I don't want to spend too much time on that. Integrating this, what do we get? Well, this left-hand side will become negative natural log of x. This side is going to equal 1/2 natural log of u minus natural log of u plus 2. Okay, and then I get a plus c that shows up. Let's use our, let's combine some things here. So this left-hand side, simplifying that natural log, I get natural log of 1 over x. On this side, if I turn this into a quotient and then bring my 1/2 up, this is the same thing as the natural log of the square root of u over u plus 2. Make sure you're comfortable with that. Okay? And then to cancel the natural logs, I need to take e to the power of both sides. So I get 1 over x equals, this is going to become c times the square root of u over u plus 2. Okay? Again, a lot of algebra that I'm skipping here. And remember, this c is technically not equal to this c. Just as a reminder, if you take e to the power of both sides, I get e to the power of this plus this. I can split that up into e to the power of this times e to the power of c, and that e to the power of c is just a constant anyway, so I turn it into a constant c that I multiply here. We've done that before, but this is just kind of a reminder. Okay? Now at this point, you have to remember that u was just a change of variables. We do need an answer in terms of x's and y's here, so I do need to substitute back something for u. And how did we define u in the first place? U came from this variable substitution, y equals ux. Notice that implies that u is equal to y over x. So I can substitute that in for all of my u's. Based on the answer that I got down here, which is off screen now, I would have 1 over x equals c times the square root of y over x over y over x plus c. I'd like to take a reciprocal of both sides here so that I get x equals, now again, the reciprocal of this is going to turn this c into a 1 over c. But that's still just an arbitrary constant, right? So that can still be written as a c. And that's, again, something you're going to see over and over again. We get very lax with how we deal with this constant of integration because it ultimately doesn't change anything by doing that. The reciprocal of this guy is going to be the reciprocal, or it's going to be the square root, rather, of y over x plus c over y over x. Let's split that up. I get x equals c times the square root of, there's going to be 1, sorry, I just realized I've been turning my 2 down here into a c right here. I don't know why I did that, so I have to try and change that. That should look like a 2. Okay, this becomes 1 plus 2x over y. Okay, now I suppose I could stop here if I wanted to. It's technically a solution in implicit form. I mean, we had an implicit solution all the way back here, but the ideal case would be to simplify this by isolating the y so we can get an explicit solution. So I'm going to try and do that. Squaring both sides, I'll get x squared equals c times 1 plus 2x over y. Remember, squaring the c is technically c squared, but it's just an arbitrary constant anyway, so I'm going to keep calling it c. Distribute the c in and start solving for y. I'm going to get x squared equals c plus 2cx over y, and then we're going to do a little solving here. What we end up with after some algebra is going to be this. Y equals 2cx over x squared minus c. Okay, this wasn't an IVP, so we are looking for an infinite family of solutions. Okay, now it's a lot of work, but again, that's fairly typical as far as one of these differential equations problems go. You saw, where was it? You saw right here, after separating variables, that you know this did reduce down to the type of equations we dealt with in 2.2. So this was a successful substitution. It helped us solve the problem. Another thing I do want to mention, you notice here that the c shows up twice, and it's the same c. It happened because we had to distribute a c into 2 different terms here, so it showed up in 2 different places. You don't, even though we were playing fast and loose, as I like to say, with the constant of integration c, it might be tempting to say, well, couldn't this 2 times c just be c? Couldn't I just absorb that constant into that constant and just call it c? And the answer in this case is actually no. The reason you can't do that is because that c is showing up in 2 different places. Remember, this c and this c are the same. And so what this is saying is that in order for this equation, or in order for this to be a solution to our differential equation, the constant up here, the coefficient on this x, has to be exactly twice as much as, or twice the size as this constant down here. If you just absorb that 2 into that, it's no longer you're no longer going to have that relationship. So that's one case where you can't absorb one constant into another like we've seen in different cases. Okay, that's going to be it for this first video. We have a couple more examples with different substitution techniques to look at, and we should be able to get both of those in the second video.